How quantum machines use machine learning algorithms. First, if we are going for quantum computing means we should learn apart from zeros and ones. First of all of you, if you want means you can close your eyes or recall in your mind what I am saying. So it will be easy to understand what is quantum computing, then what is machine learning. Then we will go for presentation. Since if we think means our capacity will increase in research. First, why we are going for quantum computing? Actually, in computer, we know all are binary, zeros and ones, like Boolean operations or anything. But in quantum, apart from that, we will have so many bits that are qubit. First, let us assume, okay, think in mind. Now I am not presenting anything from PPT. Just I am say what I am telling you, recall it. First, you take a ball or anything which inner surface should be empty. In bottom it will be 0 and up it will be 1. So this is 0 and 1. So it is an bit. If we rotate that empty vessel, if we put something inside, small thing and rotate. If we take a ball means if we put a ball rest or small ball like that, and if we rotate means that ball will rotate. In any of the place, if we take that means some value will be there. Apart from between 0 and 1, it will be between zeros and ones. So we will call that as qubit. Bit means 0 and 1. 0 and 1, top or bottom. Qubit means apart from this zeros and 1, between the value of zeros and ones, while rotating a small ball inside a big ball. In which position it occurs, that is a value. In olden days, what we use means vacuum tubes. If you see olden computers in 1980s like that, TV and all, you will have vacuum tubes, which is an NAR. It will be bigger in size, but it was developed into a transistor, which will be small. Then reducing that size, it came to very nano size. So every year it doubled from 1000 to 2000, 2000 to 4000 like that for a certain period of year. So there is a threshold. The transistor will give 0 or 1. So in certain period in 2013, it crossed the threshold. Some values are between zeros and 1. So we can't go beyond that. So we stopped increasing the transistor or reducing the size of the transistor, which means quantum computing will operate in subatomic level. We are having atomic level, proton, neutron, electron. And in quantum, we will use subatomic level, quarks, lepton, boson, etc. in different combinations. So we will have 3 important behaviors in quantum computers or quantum computing. If we go inside or in depth, like as VI, it is SEI. SEI. S means superposition, E means entanglement, I means inference. SEI. Superposition and entanglement. Entanglement is which we are placing a thing in India and in America. 2 things. While if we change or if we done anything in India, for that particular atom or that photon like that, it will be affected in America also. That is called entanglement. It is combined polarity, 90 degree. Inference. Inference means two different waves. Okay, it will be crossing various things. So to identify a particular, it will be very difficult particular position. Then we will see the superposition. Okay. Now for seeing the superposition, we will get into the slide. First, what is a quantum computer? Quantum computer is a machine. Quantum computer is a machine which performs calculation by using the law of quantum mechanics. If you are going to study quantum computing, we have to know quantum mechanics, some basics, because it will cover some mechanics, equations, formula and logics, and quantum physics, and in mathematics, some concepts like Fourier transformer, factorization, polynomial, like that are very must to learn this, which is the behavior of subatomic level particles. Atomic level means proton, neutron and electron. If it's a subatomic means, already I told, quarks, lepton and boson. It's a combination also in different. This quarks, lepton, boson are inside this electron, proton and neutron, which are very tiny. This is the history by Feynman. I think I can safely say that nobody understands quantum mechanics, said by Feynman. In 1982, Feynman proposed the idea of creating machines, which is based on the law of quantum mechanics instead of law of classical physics. Later on in 1985, David Hughes developed the quantum Turing machine, showing that quantum circuits are universal. Then in later 1994, Peter Shok came up with a quantum algorithm to factor very large number of polynomial time. In 1997, Log Grover develops a quantum search algorithm with a root of n complexity. Now the representation of data. Okay. As I already told, a bit is represented by single atom, which will be 0 or 1. Single bit, which I told while rotating that ball, big ball, inside that some small ball will be there. While rotating, we will take in certain position, that is called qubit. Between this 0 and 1 inside a ball is qubit. 0 and 1 is a bit, and between that is a qubit. In physical implementation of a qubit, okay, use two energy level of atoms. One is the excited state at the top level, and another one is the ground state is 0. As I told, that ball, bottom is 1 and up is 0. Here is the diagram. This is the ground state and this is the excited state, which is the electron. This is state 0 and this is state 1. This is the superposition, important thing in quantum computing. We all should know this psi gate. This is the important term in quantum computing, superposition, which will be psi get equal to alpha 1, 0 get plus alpha 2, 1. Okay, in this single qubit forced into a superposition of two states, which is zeros and ones, denoted by addition of state vectors, where alpha 1, this alpha 1 and alpha 2 are complex numbers. Okay, 1 square plus alpha 2 square equal to 1. Then this qubit in superposition in both of the states 0 get and 1 at the same time. It will be in 0 and 1. See here. This thing. State 0 gate plus 1 gate. This is state 0 at the same time. So this is the formula for 3-bit qubit register. Actually, we studied in digital that for 3-bit, it will be from 0 to 7. See here, this 000 is 0, 3-bit. Then this 000 is 111 is 7. So there will be 8 from 0 to 7. There will be 8. So psi get equal to 1 by root 8, 000 get plus 1 by root 8, 001 get plus. Similarly till 7. This is equally weighted superposition of all possible states, which is denoted like this. So this is the superposition equation. So please remember this. In this, alpha and beta are alpha 1, alpha 2. It can be taken as alpha or beta or alpha 1, alpha 2, which is the amplitude, probability amplitude. In general, a qubit register can represent the number 0 through 2 power n minus 1 simultaneously. Okay, 0 through 2 power n minus 1 simultaneously. If we attempt to retrieve the values represented within the superposition, if we want to take, as I told, no, from 0 will be the bottom and 1 will be the top. Once if we rotate that big ball and take that value, it will be randomly collapses to represent just one of the original values. One of the original values. Okay, as I already told, in our equation, psi get equal to alpha 1, 0 get plus alpha 2, 1 get. Okay. Actually, normally we will tell bracket. This is separated into bra plus ket. Bra is the less than symbol dot 1, which is the analogous to complex conjugate transpose of the ket. Similarly, it is the first of, then second of ket. Ket is the 1 dot greater than is the analogous to column vector. This is where I will use this get like that. If we use like this means ket symbol. After 0 and 1, I am using this bracket, this greater than 1 greater than or 0 greater than. It will be said as ket, which is the analogous to column vector. If its opposite symbol means less than, means analogous to complex conjugate transpose of the ket. Okay. Actually, if you want to retrieve the data, what I told here means, which will be the 0 is the bottom of the ball and top is the 1 of the ball. Okay. If I put a small atom or small something, small ball or tiny ball like that and rotate means, and if I want to take some value where that ball stands. In between that 1 and 0, superposition randomly collapses. In this equation, as I already told, alpha 1 and alpha 2 are the probability amplitudes. Alpha 1 is the probability of superposition collapsing to 0 get. Similarly, in a balanced superposition, alpha equal to 1 by square root of 2 power n, where n is the number of qubits as I already told. Then entanglement, already I told. If we keep two crystals, one in India and one in any other country or anywhere, what are the changes we are doing in India or in America, it will reflect in India. If it done in India, it will affect in America. That is the entanglement. Relationships among the data. Okay. Similarly for data, if you are using blockchain, data will be saved in multiple systems. So if we are updating or upgrading something in our data, means it should reflect all the systems. Then only if data is affected in one systems, it can be fetched or retrieved from another systems. This is called entanglement. Three things in quantum computing are very important, which is quantum behaviors. One is superposition, as already we saw. Then this is the entanglement. Entanglement is the ability of quantum systems to exhibit correlation between the states within a superposition. Already we saw superposition between that 0 and 1 somewhere. Now we are having, imagine, two qubits, each in a states of 0 gate plus 1 gate, a superposition of the 0 and 1. We can entangle two qubits such that the measurement of one qubit is always correlated to the measurement of another qubit. As I told, measurement of this value will be correlated to the measurement of the another value. Similarly in qubit. Then inference. Quantum waves, which mostly depends on waves. Okay. In quantum mechanics, particles like electrons and photons are described by wave functions. This wave function is the psi, already I told, which is like threshold symbol representing this state. Then superposition principle. Quantum waves can exist in multiple states simultaneously because it will go that much fast. So it will exist in multiple states simultaneously. If we take a two wall and if we shoot in a gun by tearing one rectangle shape hole, and if we shoot means what we are shooting, it will go straight and through that hole and stick in another wall. Similarly, if we tear another side and if we shoot this side, similarly it will be in straight line another side of the wall. But if we shoot on both the holes, it will not go in a straight line. There will be creation of multiple lines, since due to the reactions between these waves. So it can exist in multiple states simultaneously. Wave amplitudes add. When two quantum waves overlap, their amplitude combines following the superposition principle. Okay. Now operations of qubits, reversible logic. Due to the nature of quantum physics, what we studied in digital electronics and gate. Suppose if you are having an AND gate here, example, this is the input. A and B are 0, 0 means 0, 0, 1 also 0, 1, 0 also 0. And if we are having 1, 1, A and B, then C will be 1. But this can't be used in our quantum gates. Now we will see the quantum gates, because these are the basics while we are going for quantum computing using machine learning, quantum machine learning, QML. Quantum gates are similar to classical gates, but do not have a degenerate output. Their one original value state can be derived from their output state uniquely. They must be reversible. It's this means that a discriministic computation can be performed on a quantum computing only if it is reversible. Luckily, it has been shown discriministic computation can be made reversible by Charles Bennett in 1973. See here, this is Hadamard gate. For designing quantum circuit, it will be used. A simplest gate involves one qubit and is called a Hadamard gate. Also known as square root of NOT gate, used to put qubits into superposition. See here, this is the Hadamard gate, here one H, here one H, which is the state 0 and this is the state 1. This state is 0 gate plus 1 gates. Two Hadamard gates used in succession can be used as a NOT gate. See, first one will be the target and another one will be the control. Quantum gates for NOT gate, which operates on 2 qubits. This is the Hadamard gate, which use or involves 1 qubit. 1 qubit means Hadamard gate. 2 means controlled NOT gate, CN gate. Pair of XOR gate with some extra information. Okay, 0, 0 means 0, 0 and 1, 1 means what it will do means, see here, I mentioned here. It will depend on the A. See here, 0 and 1 means it will change, and 1, 0 means similarly 1, 0. Similarly, for 0 and 1 means 1, 1. So it's a carry. This is the thing which used in 2 qubits. Now for multiplication by 2. What I told here means 0, 0 means carry bit also 0 and ones bit also 0. For this operation, I am explaining this two, 0, 1 and 1, 0. See here, 0, 0 means 0, 0. 0, 1 means carry will be 1 and this 1 bit also 0. So this carry will become 1 addition. So here another one we will get. Now we can build a reversible logic circuits calculating multiplication by 2. See here. See here, 0, then carry bit, ones bit by putting Hadamard gate. Now a gate which operates on 3 qubits is called a controlled NOT gate, CCN. A target will be 1 and control will be C and B. Similarly, that 0, 1, 1, and that will take the action. See here, when our target input is 1, our target output is a result of NAND of B and C, NAND operation. Then we will go for machine learning. Okay. Just for a few minutes, we will recall in mind regarding machine learning so that it will be easy for learning. Machine learning. Machine means making the machine to learn. How we can make the machine to learn? Like us, when we are in young age or in child, we will learn everything. Similarly, we have to make the machine to learn. How it can be done? By training. By training. Okay, this is the important thing, training. Data set. Data means data. What? The food. Showing the food to the baby, it will identify that that is the food. Showing the water, it will identify that it's a water. Like that, we have to train the machine by visualization or hearing or smelling. Like that, we will learn. Similarly, the machine has to learn. For that, they will use data set. Like visualization means images, then text, like that. There are different types. In this, there are three types. One is supervised machine learning, unsupervised, and reinforcement. Now, let's see in slide. What is machine learning? Learning is the process by which system improve its performance. First, we will train the data. For small baby also, what we will do? We will train them for walking or anything. We will train. Similarly, we will train the machine using data. Then learning algorithm. Then it will become a trained machine. After that, if we give a query, then we will get the answer. Then supervised learning. In machine learning, there are three things: supervised, unsupervised, and reinforcement. In supervised learning, we are having classification, regression, and estimation. Similarly, in unsupervised learning, we are having clustering and prediction. Similarly, in reinforcement learning, we have decision making. Supervised learning. First, we will see example. It will be easy to understand. Then we will come to this theory part. See here. Supervised learning. As I told already, it's an classification and regression, which is classification means define labels and regression means no labels defined. See this supervised learning. First, what we will do? We want to identify the duck, so we will train the machine using different duck images and the tortoise images or what are the not similarity images, and we will name that as not duck. Then after the supervised learning, it will become the predictive model. Then if we give some image means it will compare with this and it will tell that if it's true means it will give duck or it will show some other what is unwanted. This is unsupervised learning. Whatever we are trained, it will get the output. Then the reinforcement learning. First, we will have agent and environment. By seeing this short example, if you are having a dog and daily, if this environment throws the ball, then after that this dog will pick the ball and give, then it will be feeded. Similarly, if it's done multiple times, means automatically if he throws the ball, it will be feeded. It will bring the ball, then it will be feeded. That is the rewards. Rewards is the feeding, food. Observation means ball is thrown, then it has to act, that it has to bring the ball. This is the reinforcement learning. It's okay, or some more thing want to be learned from machine learning? Okay. First, in computer, if you are placing the photo, in that tree is present or not, it should identify. For that, what we have to do, there are two types, which is data driven approach or procedural approach. Data driven approach. For that, data driven. Okay, data means what? We have to train that is 1000 or 100 trees. So it will identify that tree is present. This is tree, like that. Then procedural approach. Procedural approach means it may not be possible. If we trained using stem, fruits, leaf, root, etc. What? Some trees will not have leaves in summer season. Some trees will not have stem. Some will not have fruits in some season. Okay, understood? Data driven and procedural approach. Data driven means if you want to identify the trees in a photo, we have to train it with 1000 trees or 100, like that, of photos. That is data set. Then procedural approach. Two types. One is data driven, another one is procedural. Procedural means stems, fruit, leaf, means it can't be possible because some may have stem, some may not have fruits. In some season it may be there, or in some seasons it may not be there. Okay, some are another examples. Email. In email, it has to identify spam or not. Spam or not. Similarly, in Amazon or Flipkart, if you are purchasing some product, okay, if we see down or in that site or app, means it will recommend something related to that, or some persons who purchased these things also purchased these things, like that it will recommend. Similarly, also human vital parameters like diseases present or not. In machine learning, we are having two things. One is data driven and procedural approach. Also, weather prediction. Today it will rain or not, or in future after 7 days, like that. Machine learning is a fun learning. Okay. If we write a program and behave to that program, algorithm given and predict and replay. The ability of a computer to learn without explicitly program. Some other example also we will see. Okay, we have to count apple or orange. We have to be careful. Okay, in this. Okay, what we can say by seeing the orange color, orange, orange, or red color, or red pixel means in the image it's apple. Okay. Similarly, if the given input is black and white, then how it can identify the red pixel or orange pixel? It may be difficult. What will be the behavior of the algorithm for creating red and orange pixels? So we use classification function which takes input and classify and labels the data as output. No, actually I am not telling from this slide. I am telling with my experience or already I learned. Two things I said now. What means one is machine learning is the fun learning. Actually, we are having if we want to identify a tree in a photo, it should be trained with trees. Okay, that is data driven approach. It's trained with data. Then procedural approach. Procedural means we will train with fruits, leaves, stems, etc. In voice also breaking. Now it's okay, sir. Voice is clear. Now my voice is clear.
Yes, sir. Yes, sir.
Okay, okay, okay. Now we learned quantum and also the machine learning. Now we will go for quantum machine learning. Okay. Are you hearing?
About quantum computing applications in machine learning. This is a very exciting area of quantum computing research, and lots of classical machine learning developers are excited about the potential applications within their own field. Today, I'm going to talk to you about quantum computing applications in machine learning. This is a very exciting area of quantum computing research, and lots of classical machine learning developers are understandably excited about the potential applications within their own field. So to get started, let's talk about a classical machine learning problem that is one that's very common, linear classification. So if we start with two sets of data that we want to classify into two separate categories, let's draw them here. We're just going to have 3 dots and 3 crosses, all on a single linear plane here. If the data is arranged like this, it can be pretty easy to classify this into two discrete groups. We can draw a single line in the middle here, and now we've classified them. But this can be a lot harder if our data is more complex. For example, if our data is arranged like this, perhaps with the crosses in the middle, now there isn't a single line that we can draw on this plane to classify the data into two discrete groups. So in order to solve this problem and classify this data, what we need to do is we need to map this data into a higher dimensional space, which we're going to call a feature space. Then, if we've mapped the data, for example, like this, we can now see, because we've mapped this data into a higher dimensional space, there is now a much easier way to classify this. So how do we do this step of transferring our data, mapping it into a higher dimensional feature space? To do this, we can use kernel functions.
Kernel functions work by taking some underlying features of the original data set and using that to map those data points into this high dimensional feature space. Kernel functions are incredibly powerful and incredibly versatile, but they do face problems. Sometimes they just give poor results, and also the compute runtime can explode as the complexity of the data sets increase. If you're an experienced machine learning developer, perhaps you've seen this already if you're dealing with data that has very strong correlations, or perhaps if you're dealing with time series forecasting where the data is very complex and at a high frequency. But quantum computers have the potential to provide an advantage in this space. They can be useful because quantum computers can access much more complex and higher dimensional feature spaces than their classical counterparts can. And they can do this because quantum computers we can encode our data into quantum circuits, and the resulting kernel functions could be very difficult or even impossible to replicate on a classical machine. As well as this, those kernel functions also can perform better. In 2021, IBM researchers actually proved that quantum kernels can provide an exponential speedup over their classical counterparts for certain classes of classification problems. As well as this, there is a lot of research going into improving quantum kernels with structured data and kernel alignment. So as you can see, this field is incredibly exciting. There's a lot of research going on in this space. And you can use Qiskit runtime to easily build quantum machine learning algorithms with built-in tools such as the sampler primitive, which primitives are unique to IBM's Qiskit runtime. These are essentially predefined programs that help us to optimize workflows and execute them efficiently on quantum systems. Let's take, for example, our linear classification problem. Let's say we have our data and we've encoded it into a quantum circuit. We can then use the sampler primitive to obtain quasi-probabilities indicating the relationships between the different data points. And these relationships can constitute our kernel matrix. And that kernel matrix can then be evaluated and used in even a classical support vector machine to predict new classification labels. So if you're ready to get started learning more about quantum machine learning, you can check out the links in the description for more information about Qiskit runtime, as well as a quantum machine learning course that's available on the Qiskit textbook. I hope you've enjoyed this content. Thank you very much for watching.
This is the ML process. Is my voice audible?
Yes, sir.
Okay, sir. First is data acquisition, then data cleaning, because we will get noisy data or missing values like that. We will clean the data, then we will train the model, then after that we will test the data and the model will be deployed. This is the machine learning model. Then now we will go for quantum machine learning. Okay. This is a method of combining the quantum computing and machine learning. See here, this diagram. One side is data, which is classical and quantum. Similarly, another one side is algorithm, which is the classical and quantum. Okay. Actually, we can plot this like this. Data CC. Data is classical and algorithm is classical. Then similarly, data is classical and algorithm is the quantum. Similarly, the data will be quantum and which will be classical algorithm. Then here we will have quantum data and quantum algorithm. That means classical data, first this classical data being processed classically. Here this quantum, using quantum computing, here the data. So quantum data which will be processed by using classical computers. See here, using quantum computing to process classical data sets. Then here both are QQ, quantum data being processed by quantum computers, which was taken from the Supervised Learning with Quantum Computers Springer 2018. Here what we see, QC. So we will see one example, QC. Quantum data being processed by classical computers. Q means quantum and C is the classical. QC case. This is explored quantum entanglement using machine learning approach. Okay. As I told no previously, entanglement. Here we are having state space. Which is PPT criterion. PPT means positive partial transpose, which is a separable state, must have a PPT. See here, separable state means we can separate that. This and this positive partial transpose both can be separable. It is necessary sufficient when dA dB less than or equal to 6. dA dB which will be less than or equal to 6. Okay, whatever I am saying, just listen. Mostly there will not be slide here, but whatever I know, I will tell. This is the separable state. Okay, separable. Okay, in this partial transpose, this partial transpose is a mathematical operation. Okay, which is applied to part of a quantum state. Example, only Bob state. Partial transpose means mathematical operation applied to the part of quantum state. Only Bob part. Then this transport. First, what we saw? Partial transpose. This partial transpose. Then this transposed state. Transposed state, no negative eigen values, it's still positive. It's still positive. Which state is said to be positive partial transpose? Then entanglement witness. Or this positive partial transpose itself dA dB less than or equal to 6. For small system, it's a sufficient conditions. This means PPT is a separable state. Here in small system we can separate like this. For larger systems, dA dot dB which is greater than 6, a state can have PPT but still be entangled. PPT is not positive partial transport is not enough to prove separability for larger system. For smaller system we can separate state, separable state. For larger systems it is difficult. Then we will go for entanglement witness. Entanglement witness is a mathematical operator designed to detect a quantum state which is entangled. It works by identifying which a given state is outside the set of the separable states. Entanglement state means which will identify given state is outside the set of separable state. For this we will use equation PR W dot sigma greater than or equal to 0 for all separable state sigma. For rho which is less than 0 for the target entangled state. If you are having different kind of entangled state means which require different witness, because the geometry of the entangled region in state space is complex. In state space is complex. Okay, state space. Okay, state space means a quantum system which contain all possible quantum states. It has two important regions. Okay, state space means which has two important regions. One is separable states and entangled states. Separable state means a convex rounded set of where states have no entanglement, no entanglements. Entangled state means outside the separable region showing quantum entanglement. See here, we are having a bubble. Okay, inside these are separable states, outside these are entangled states. Do you understand? Inside these are, this bubble are separable states, outside these are entangled states. Entangled witness are like probes that poke into bubble to check if a state is inside separable or outside entangled. Inside means in the separable region like this. Here means which is separable state. Here means these are entangled state. Do you understand this QC case? This QC, quantum classical. This QC, quantum classical, which is a methods of detecting biparticle entanglement, biparticle, two particles, which is a positive partial transpose and entanglement witness, which is state space, separable and entangled. Separable means no entanglement, convex rounded with no entanglement. The bubble inside are separable and outside are entangled states. Next we see some CQ cases. CQ. CQ means classical data and quantum algorithm. For this quantum computing helps in machine learning. The core idea for this is CQ. For a learning problem, the input which are having high dimensional vectors of numbers like text or images, which will be high dimensional vectors in numbers, which required number of qubits is only logarithmic in dimension. This is the vector. V belongs to R power D tends to V belongs to R power D tends to log 2 dimensional qubit state. We get equal to 1 by V modulus of summation I to D, I equal to 1 to D Vi of I get. So we want to efficiently represent our data in quantum states and apply quantum algorithms on them to learn. I will explain this equation. Okay, listen it carefully. This V tend to R power D. Okay, a vector in D dimensional, a vector in D dimensional real space to a quantum state in a log 2 dimensional qubit state. This is the common technique in quantum machine learning. So only I am saying this equation in detail. Okay. QML to encode classical data. What this classical data will be converted to quantum states for quantum computations. But first in machine learning, what we will get classical data, which to be converted into quantum states for quantum computations. For this, we are using these equations we use. Okay. V belongs to R power D is the vector in a D dimensional real space to a quantum state in a log 2 D qubit system. Okay. Now we will see the vector mapping. Vector mapping means V belongs to R power D, which represents the real valued D dimensional vector. Real valued D dimensional vector. Then this quantum states. Okay. This log 2 D. This vector V is normalized and encoded as a quantum state V. This V is normalized and encoded as a quantum state V. See here. In a log 2 D qubit system. Then normalized quantum state, this part, this blue part. We get equal to 1 by modulus V summation of I equal to 1 to D Vi of I get. Here this modulus of V, the norm of the vector V used for normalization. Then this summation of D I equal to 1 to D Vi of I get. This is the quantum superposition, okay, of the basic state I get, which coefficients this Vi derived from the vector components. Do you understand this equation? If you want means I can tell again. V belongs to R power D, represents a real value D dimensional vector. Why we are using these equations means this is the common technique used in quantum machine learning to encode the classical data into quantum states for quantum computations. V belongs to R power D means represents the real value D dimensional vector. This quantum state, okay, in quantum state vector V is normalized and encoded as a quantum state, this we get. In a log to d qubit system, then the normalized quantum state, this blue color, we get equal to 1 by modulus of v summation of I equal to 1 to d vi slash vi I get. Here modulus of v, the norm of the vector we used for normalization. This summation of I equal to 1 to d vi I get means a quantum superposition of the basis states I get with coefficient vi of coefficient this vi derived from the vector components. Now we see some applications of quantum machine learning, feature encoding, quantum kernel methods, quantum neural networks. Then we will go for quantum associate memory, which means this CQ, this CQ. Classical data and quantum algorithm. Associate memory means which stores a set of fundamental memories like epsilon 1, epsilon 2 till epsilon m. When it presented a new pattern X, the system output one of the stored memory that is most similar to X. Stored memories that is most similar to X. Why we are using this quantum associate memory? The main purpose of this quantum associative memory is to build by Ventura and Martinez is pattern completion, where the full pattern can be restored from partial pattern. Full pattern can be restored from this partial pattern. The memory use a storage algorithm and Groover's quantum search algorithm. Here the memory use storage algorithm and Groover's quantum search algorithm for retrieving the patterns. Here we use two types of quantum associative memory. One is for preparing superpositions of input and another one is retrieves the patterns. This is the algorithm. Which is taken as I told already here, which is built by Ventura and Martinez, is pattern completion. This is the algorithm, refer from that I mentioned here, Ventura D, Martinez T quantum associative memory. In 2000, 2000 it was published. With 2 n plus 1 qubits, the QAM can store up to n equal to 2 power n patterns, where n is the total number of basis states in 0 m1 steps and requires O of root 10 time to recall a pattern. Now I will explain this algorithm. In any quantum initial state, we will take psi gate equal to 0 bar gate. Okay, start with a initial state, generate an initial state. Okay, psi, where all qubits are in 0 state. 0 gets state. This serves as the starting point for memory system before we begin processing data. Then this for m greater than or equal to p greater than or equal to 1. This is more mathematical. for mathematical department like this, there are various department involved in this. So it will be very difficult if we are listening first time like that. So I am sorry for that, because it will be very difficult. If we see multiple times only, it will be recalled. Okay. Then this for m greater than or equal to p greater than or equal to 1. This is the mapping function. Okay. Operation to encode a memory pattern into a quantum state. Memory pattern to a quantum state. This step loads the data like a pattern or feature vector into the quantum system, preparing for further operations. Then this flip step, which applies a quantum gate, bit flip or phase flip, bit flip or phase flip to state psi. Flipping the state adjusts it to reflect specific properties or patterns to store in memory. Then this escape p psi get. This is the subroutine or operation that encodes more data or transform the state in some way. It helps in refining or manipulating the state to better represent the desired memory pattern. Then save psi get. Save the current quantum state psi get here as a reference for future operations. It ensures that immediate results can be reused or checked during computation. Then this will be repeated multiple times, t times. This decap psi get. This is the quantum operator. This is the quantum operator decap, a transformation or gate to the quantum state psi. This step update by modifying the gate gcap, possibly encoding or processing the memory further. This I cap p psi gate. Prepare the quantum state using an operator I cap which encodes some data or pattern, which create a new quantum state which is compared or associated with psi. Simple explanation for this algorithm. We have started with a blank quantum state initially, psi get equal to 0 gate. Then this is encoded patterns. Then it is flipped the state using quantum gates. Then we saved intermediate states for later use. Then use of operator, process, compare or refine the memory states. This process is repeated for multiple times to ensure the memory accurately stores and retrieve information. Why we are using this algorithm means the quantum system which stores and recognizes not get as I already told this not gate, C not gate and all, this is similar. This is the venture and Martinez gate. Is it Toffoli gate? Then quantum pattern classification. Another example of CQ case. Shinaski petition SSP algorithm, quantum nearest neighbor algorithms, which uses k neighbor algorithm like machine learning. This is referred from here mentioned Ablayev, Farid et al. On quantum methods for machine learning problems part 2, quantum classification algorithm, which is similar to KNN. This algorithm is the quantum version of classical weighted nearest neighbor algorithm. If n is the size of input vector, m is the number of input vectors in training set, d is the number of classes. Properties of this algorithm SSP means Shinaski petition k nearest neighbor by for classifying the test vector. Size of SSP KNN equal to 2n plus log d plus 1. Similarly, time SSP KNN preliminary stage, then the time SSP KNN main stage. These are the steps. Step 1. We prepare the superposition of all the training vectors into one quantum states. This is the T gate equal to 1 by root m summation of j equal to 1 to m xij to yij. Then the initial state is prepared. Psi naught gate equal to 1 by root of m summation of j equal to 1 to m x1 to yj comma 0 gate. Then we are applying the ATAL gate to utility qubit. Psi 1 gate equal to 1 by root m j equal to 1 to m summation of x1 to xn x1 j power j to xn power j comma y power j into 1 by root 2 0 gate plus 1 gate. Then step 4, apply C naught gate and NOT gate. This is the NOT and C naught. Similarly, for this above equation, we are applying NOT and C naught. See, this is the training vectors. Then we are preparing initial state just comma 0. Then with that we are adding ATAL gate. Okay. So what we are using into 1 by square root of 2 0 gate plus 1 gate. Then with this we are adding this C naught gate and NOT gate in front. Similarly, step 5, apply the unitary vector. We are applying unitary vector. After that, applying a ATAL gate on a utility qubit and write the phase information on jth state into amplitudes. Then 7th step, measure the utility qubit. Why I am running means time is 7:25. Within 5 minutes I have to close. So only I am running. Measure the utility qubit. If the test vector is close to the training vector, then the probability of a 0 result is high. Otherwise, the probability of 1 result is high. Similarly, the 8th step, if you obtain a 0 result, then the next step is to measure the class register. The probability of obtaining C result from the class register measurement is represented here. Then CQ applications, implementation of entanglement measure. This is the implementation of entanglement measure, which is referred from the Zaid Muhammad et al. Quantum classification algorithm based on competitive learning neural network and entanglement measure. The MZ is the unitary operator that applies the C naught gate between the qubits U gate and V gate, followed by measuring the degree of entanglement in between the operator D. Then the state of qubit U gate is arbitrary. then state of qubit we get initialized in vacuum state 0 get. For the state uv get equal to alpha psi 0 get plus infinity 1 1. The co-occurrence measure is as follows: QQ case, which is the k nearest neighbor. Supervised machine learning KNN classification based on measure of similarity. The similarity, more similarity means it will be in center, which will be grouped, and again then k equal to 1, k equal to 3, then k equal to 5. Similarly, it will be circled. Then the test state with the known label is compared with the training state. K number of state neighbors for the train state are identified for the given test state. This label test state is determined upon majority voting, which is referred from 2022 Bashir Afrad and Sandeep K. Goyal Quantum K Nearest Neighbor Machine Learning Algorithm paper, research paper. Similarly, this is the classical and quantum KNN algorithm. Determine the distance between the test state and all the training state. Here, quantum K nearest neighbor is the quantum analog of classical KNN algorithm. Each state train or test is represented by a vector or complex numbers. Distance between the test state and all the train state are simultaneously calculated using superposition properties of the quantum states and collapse of wave function upon measurement. Classical KNN algorithm has complexity of OMN with n dimension vector to be classified and m cardinality of set of train vectors. Here we use swap test is used to calculate the fidelity simultaneously between the test state and all the train states. This makes quantum KNN algorithms much faster than its classical counterpart. Similarly, these steps, different types of distance measures: Euclidean distance, then cosine similarity, then fidelity. Similarly, the step 1 initialization, step 2 state transformation, and step 3 measurements. These are the initialization R1, R2, register 1, register 2, register 3, register 2. R1 is the prepared in 0 gate, then this is the psi gate, then 0 gate cross n, which n log n, then which m equal to log m, then R 0 gate psi gate, 0 gate cross n, 0 gate cross m. Thank you so much. Thanks for your attention. Any questions, please?
Thank you so much, sir.
Thank you, sir. Any feedback, sir?
So if you have question, participants, if you have any question, please use the chat feature. Now,
1 minute, sir. 1 minute, sir.
thank you everyone for your active participation and engagement in session 3. A big thank you to Dr. B. Zilwan for his insightful presentation on quantum algorithms for machine learning. Thank you so much, sir.
Okay, sir. Thank you, sir. Actually, I had a practical also, but there is no time. If any opportunity next time means, I will take that also. Here
Okay,
is
sir.
the
Okay.
demo for that. Okay, sir. Thank you so much, sir.
Thank you
Thank
so
you
much, sir.
for patience of the audience. Thank you so much.
So please stop share your screen. Good evening, everyone, and welcome back to day two of our faculty development program on quantum machine learning, bridging the gap between quantum computing and AI. In this In this session, we are thrilled to explore the topic quantum information processing application. This session will delve into the diverse and practical applications of quantum information processing, a critical component for leveraging the true power of quantum computing. Our distinguished speaker for this session is Dr. Satyabrat Adhikari from Delhi Technological University, Delhi. Dr. Adhikari is an accomplished assistant professor at DTU Delhi, specializing in quantum information processing. He holds a BSc and MSc in mathematics and applied mathematics, respectively, from Calcutta University, achieving first-class distinctions in both and a PhD in quantum cloning and quantum deletion from Bengal Engineering and Science University, with extensive postdoctoral experience at esteemed institutions such as SN Bose National Center for Basic Sciences and Korea Advanced Institute of Science and Technology. Dr. Adhikari has also served as faculty at IIT Jodhpur and BIT Mirza before joining DTU in 2017. His research focuses on quantum entanglement, teleportation, cloning, and cryptography, reflected in 62 impactful publications. Dr. Adhikari is a recipient of multiple prestigious research awards, including DTU's Premier and Commendable Research Awards, and serve as a reviewer for renowned international journals, contributing significantly to the advancement of quantum technologies. Dr. Adhikari is a well-respected figure in the field of quantum technologies and quantum information theory. With years of research experience and expertise in quantum applications, he will guide us through the transformative potential of quantum information processing. So without further delay, let us welcome Dr. Satyabrat Adhikari sir to begin this session. Be sure you will find his insights both enlightening and inspiring. Over to you, Dr. Adhikari.
Good evening to all of you. Thank you for the nice introduction. So, first of all, I would like to thank the organizer for inviting me here to deliver a lecture on quantum information processing and application. So, is my screen visible?
Yes, sir.
Okay, thank you. So, hope I'm audible also. So, my title of my talk, the title of my talk is Quantum Information Processing and its Application. So, basically, I am from mathematics background. So, you will find a lot of mathematics in these talks. But side by side, I will talk about the physical implication of those mathematics, and I will talk about the entanglement and how to detect the entangled state, and side by side I will tell you that what would be the possible experimental realization of the entanglement detection scheme. So basically I will take here there are actually entanglement detection problem is a NP-hard problem, and not a single method is available to detect all the possible entangled state in higher dimensional system, or in fact in lower dimensional system also. So so I will talk about I will tell you that what are those possible methods of detecting the entanglement, and then I will concentrate on two possible approaches. First of all, I would like to tell you about the partial positive partial transposition criteria, and then I will talk about the realignment criteria and their possible implementation possible implementation of them in the experiment. So to start with, so let me give you the introduction to quantum entanglement. So quantum entanglement is a feature of quantum mechanics which has no analogs in classical mechanics. So it is only appeared in quantum mechanics. Okay. So in the field of quantum information, these aspects of or this property of the quantum entanglement, which plays a major role in quantum information theory. So not only that, entanglement, the theory of entanglement also gives us a useful resource, in the sense that we can use entanglement in doing many things in the quantum world, which are almost impossible in ordinary classical world. Okay, so some of these tasks here I have listed. Quantum computing. So in this task, quantum computing, we can use this quantum entanglement. So in the last talk, we had already seen that this role of quantum entanglement in the quantum algorithm. So here also we have some work done on this Grover's algorithm, and we have shown that how entanglement play a role in Grover's algorithm. So you can find this paper in the archive. And then after quantum computing, you can see that we can use quantum entanglement in teleportation. So the teleportation is basically an idea of teleport a state from one place to another place with the help of this entangled state. Okay. So actually the concept of teleportation is that how we can send message from one place to another place better than the classical world. Okay, so in the classical world, we can send message with some probability, with some fidelity, and the fidelity is 66%. Okay, so with 66%, if we send if we encode some information in the quantum state, and then if we would like to send this quantum state to some other places just using the classical resource, then we can find that using the classical resources, one can send the quantum information contained in the quantum state is 2 by 3 only. Okay, that means 66.6% approximately. So now the question is that can we do better in if we use quantum mechanics? Yes, the answer is yes, we can do better if we use entangled state, which is the only property or only characteristic that only appear in the quantum mechanics, not in the classical mechanics. Okay, so in this paper, these parental papers by Bennett et al. In 1993, they have shown that we can use quantum entangled state to send the quantum state with unit fidelity. That means whatever we would like to send, we can send it basically the same thing sent to some other appear. Means the quantum state vanishes from one places and reappear to other places. And in this journey, the information is not lost at all. That means the state which we would like to teleport, it is the same state received by the receiver. So the fidelity is unit fidelity, and it happens only because of this entangled state. And then quantum cryptography. The third point is quantum cryptography. We can use this quantum entanglement concept in quantum cryptography also. And after that, let me tell you the definition of quantum entanglement. For the completion of this talk, we have to start from the definition of quantum entanglement. Maybe you know the definition, but for the completeness, I am repeating this thing. So let us consider the two subsystems A and B, which is described by the Hilbert space HA and HB respectively. So you know that the state space. The state space is the Hilbert space, and the quantum state is residing in this Hilbert space. That means this Hilbert space can be considered as a home to the quantum state. So if we consider the two subsystem A and B, then the composite system, that means if we combine these two subsystems, then we can have a composite system, and this composite system is described by the tensor product of the two Hilbert spaces HA and HB, which is defined or described by HA tensor HB. So the quantum state may arise in two forms. It may appear in a pure state form, or it may appear in the mixed state form. So I am giving the definition of entanglement in both of these two forms. So a pure state psi AB, so Kate psi, this represents a vector in the Hilbert space HA tensor HB, and this vector is said to be a separable state if if any state in the composite system HA tensor HB can be written like this: psi 1A tensor psi 2B. This means that we can write the state in individual Hilbert spaces. So if we factorize this state, then we can say that this state is separable. Otherwise, this state is entangled. So this happens in case of pure state, and in case of pure state, it is described by a vector. So you can easily see this thing, that we can write the tensor product of two subsystems in this factor form. But when we come to the mixed state, then it would be difficult for us to discriminate between the separable state and entangled state. Okay, so a bipartite mixed state described by the density operator rho is entangled if it cannot be expressed in this form, that is summation over I pi rho I A tensor rho I B. What does this mean? This means that if we take the convex combination of the product state, okay, so rho I A, that means the system in the subsystem A, and another quantum state rho I B, which is the side in the Hilbert space HB. So if we take the tensor product of these two state, then we can say that this state is in the product state. And if we are considering all the product state and then take the convex combination, so here you take the convex combination means the summation over I pi must be equal to 1. If summation over I pi not equals to 1, then we can say that it is not in a convex combination. So if we write a given bipartite mixed state in this form, summation over I pi rho I A tensor rho I B, then we can say that it is a separable state. But if we are not able to write this state in this form, then we can say that it is an entangled state. Okay, so now the question is that how we can discriminate between the entangled state and the separable state if some state is given to you. Let us suppose if some state is given to you. Okay, so how you can recognize that this given state is an entangled state? This is the entanglement detection problem. Okay, so this definition too, it will not help us not very much. It will not help us a lot, but it will just tell us that if this state is represented in this form, then we can say that this state is separable state. But one thing you should remember, a state can be written written in terms of basis. Okay, so there, suppose the state is written in this form in one basis, then you have to check for all the bases the state can be written in this form, because there exist infinite number of bases, and one basis, we can go from one basis to another basis just by operating an unity transformation on it. Okay, so just make a unity transformation, just apply unity transformation on one basis, then you will get the other basis. Okay, for example, computational basis, which is 0 1 basis. So let us suppose if the state is written in the 0 1 basis in this form, and if it is not written in the Hadamard basis, that means a given state which can be written in this form in a computational basis, but if it is not written in this form in some other basis which is a Hadamard basis. And since we are getting at least one basis that the given state cannot be written in this form, then we can say that this state is entangled. Conversely, if we can write the given state in this form for every basis, then we can say that this state is separable state. But as I said, that there exist infinite number of bases. That means to check this separable, to check whether the given state is separable, you have to check for all such bases. Okay, that means you have to check infinite number of times, which is not possible in reality. Okay, in principle it is not possible. In principle it is possible, but in reality it is not possible. Okay, so this means that this definition will not help us to discriminate between the entangled state and separable state. So now let me give you this example. Let us suppose a state, this 2-qubit state, which can be written in this form: alpha 00 plus beta 01 plus gamma 10 plus delta 11. So this is an example of a 2-qubit state. So let us suppose this state is given in this form. And mod alpha square represent the probability of collapsing the state on the basis 00, on the state 00. Mod beta square gives the probability that the state, when you measure the state psi AB, then it collapses onto the state 01. Mod gamma square gives you the probability that the state collapses onto the state 10. And similarly, mod delta square gives you the probability that the state collapses onto 11, state 11, when you perform some measurement on psi. So since mod alpha square, mod beta square, mod gamma square, and mod delta square all represent the probabilities, so the sum of all the probabilities must be equal to 1. So that is why it is this restriction. Okay, so now if we choose alpha equals to 0 and beta equals to 0, so this alpha and beta, gamma, delta all belong to the set of complex numbers. Okay, so if we choose alpha equals to 0, beta equals to 0, then the state psi AB reduces to this one. So just put here alpha equals to 0 and beta equals to 0, then you can see that we end up with gamma 10 plus delta 11. So this means that you can just write the state gamma 10 plus delta 11 in the form given in equation 4. So just from the definition, you can see here that the two subsystem can be written as a tensor product of the two subsystem A and B. Okay, so this means that two subsystem can be separated. Since the two subsystem can be separated, so we can say that this state psi AB is a separable state. Okay, now let us suppose we can choose alpha equals to half, beta equals to half, gamma equals to half, and delta equals to half. In this case also you can see that the two state can be written in this form, which is given in equation 5. So this means that in this case also the state is a separable state, because it can be written in terms of the two subsystems separately. So let us suppose if we choose beta equals to 0 and gamma equals to 0, then you can easily see here that alpha 00 plus delta 11, and you cannot factorize it. Okay, so that means you cannot write the two subsystem independently. And since you cannot write the two subsystem independently, this means that the state cannot be separable. This state is an entangled state. Okay, so this is the very easy thing for the pure state. But as I have said, that when you come to the mixed state, then it will be very difficult problem. That is, the entanglement detection problem is very difficult for the mixed state. If some bipartite mixed state is given to you, then it would be very difficult for you to say whether the given state is entangled or separable. So there are some methods for the detection of entanglement. The first method is that positive partial transposition criteria. This method is very useful method to detect the for the detection of entanglement, and this method is given by Perez and Horodakis, okay, independently. So this method tells us that if we take so okay, fine, so I will come to this point later. So let me first read these methods for the detection of entanglement. So the second method is computable cross norm and realignment criteria. The third one is range criteria, and fourth one, we can construct positive but not completely positive map. And this complete positive map is we can use this positive map to detect entanglement. Okay, but the problem is that if we were considering the positive map only for the detection of entanglement, this positive map can work theoretically, but you cannot apply it in the experiment because it cannot be realized. Okay, so my talk will be on this, that how to realize the positive map. Okay, how to make it completely positive map, because a positive map which is not completely positive map, that can detect entanglement. Okay, but if we make the positive map, and also if we do something on the positive map, So that we can realize it on the experiment, then we have to perform some operation, okay, on the positive map. And those operations, when you perform the on the positive map, it reduce or it takes into the completely positive map, okay. And we know that when we have a completely positive map, then it can be detected, it can be realized in an experiment. But the problem is somewhere somewhere in different places, which I will mention in my later slide. So the next criteria is measurization criteria, and then covariance matrix criteria, and then some approaches through the construction of witness operator. This the last approach through the construction of witness operator. This is a very good approach to detect entanglement. Why it is good? Because this can be realized in an experiment. It can be you can work on you can work theoretically, and you can construct witness operator theoretically, and then this witness operator can be realized in an experiment also. So this approach is better, in the context of quantum technology. So these are the methods that may detect the entanglement. So I will concentrate on those on the two criteria. First one is the positive partial transposition criteria, and the second one is the second listed here, that is realignment criteria. So I will talk to you about this in detail. So what do you mean by partial transposition? So here, positive partial transposition criteria. So first of all, we would like to know that what do you mean by partial transposition. So we already know, if we have some matrix, then we can how transposition operation work. But do you know that how this partial transposition work? So here I will give you some idea that how partial transposition works mathematically. So let us suppose we have any arbitrary 2-qubit density matrix, which is given by this 4x4 matrix. So any arbitrary 2-qubit density matrix is described by this 4x4 matrix, and this 4x4 matrix can be divided into 4 block matrices. Okay, so here you can see that A, B, B dagger, and C, they are block matrices, which is a 2x2 matrices. Okay, so now what do you mean by the partial transposition? So partial transposition of this 4x4 matrices is defined by equation 8. So just look at equation 8. So here what we have done, we have just take the partial transposition with respect to the system 2. Partial transposition means we are doing the transposition operation on any one of the subsystem. Okay, so in the 2-qubit system, we have 2 subsystems. Okay, so now the partial transposition means that we have to perform this transposition operation on one of the subsystem. You can operate on either subsystem A, or you can operate on either on subsystem B. So mathematically, how we can describe it? So we can describe in this form. Okay, so just take the partial, you can take the transpose of each block matrices. Okay, so here A, B, B dagger, and C are the block matrices. So partial transposition means just take the transpose of this block matrices. So when you are taking A transpose, that means T11, A matrix is given by T11, T12, T12 star, T22. Just take the transpose of this A, then you can get A transpose and write in the right hand side of equation 8. So the resulting matrix in the right hand side of equation 8 is the partial transposed matrix. Okay, so now I can explain you the what do you mean by positive partial transposition criteria. So positive partial transposition criteria tells us that first of all, let me say you that the row 1 2, which is given in equation 6, it is a density matrix. So it is a density matrix. This means, what does this mean? The density matrix means that this matrix is a Hermitian matrix. That means row 1 2 equals to row 1 2 dagger. This is the first thing. Second is row 1 2, trace of row 1 2 must be equal to 1. So that means if you considering the trace of this matrix, density matrix, then it would be equal to 1. Why? Because T11, T22, T33, and T44, these diagonal elements represent the probabilities. Okay, so if you add all the probabilities, then it must be equal to 1. So trace row 1 2 equals to 1, And the third thing is that, which is the most important point in this matrix, is that row 1 2 must be positive semi-definite matrix. Okay, so row 1 2, the density matrix must be positive semi-definite matrix, means that all its eigenvalues must be non-negative. Okay, so this is the properties of the density matrix. So now if we perform some operation on it to determine whether the state described by the density matrix row 1 2 is entangled or not, Perez and Horodiaki applied the partial transposition criteria. Okay, so partial transposition criteria states that if you perform the partial transposition on row 1 2, then the partial transposed matrix, if the partial transposed matrix gives one negative eigenvalue, then the state is entangled. Okay, and the converse is also true. The converse is that if the if and only if condition is can be stated in this way, that if the state row 1 2 represent a separable state, then row 1 2 T2 must be a positive semi-definite operator. Okay, that means row 1 2 T2, and that means partial transposed matrix must be a positive semi-definite operator if the state is separable. So if the state is separable, then row 1 2 T2 is a positive semi-definite operator. And conversely, if the positive if row 1 2 T2 is a positive semi-definite operator, then this state is separable. So this necessary and sufficient condition only hold in 2 tensor 2 system and 2 tensor 3 system. Okay, so that means qubit system and qubit system. So in these two system, the positive partial transposition criteria is the necessary and sufficient conditions, or necessary and sufficient criteria. Okay, but for in higher dimensional case, it is only necessary but not sufficient. Okay, so this means that if this state is separable for higher dimensional system, if this state is separable, then row 1 2 T2 must be greater or equal to 0. But you cannot say the converse is also true in the higher dimensional system. That means if row 1 2 T2 is greater or equal to 0, that means all eigenvalues of row 1 to T2 are non-negative, then you cannot say for higher dimensional system that the given state is a separable state. Okay, so this is the thing in the context of positive partial transposition criteria. So now, like positive partial transposition criteria, so you can see here that in the partial transposition, so we have we are rearranging the matrix elements in some particular way. Okay, so here also we can do the same thing in case of realignment of a when we are considering the realignment of a density matrix. So when we are thinking of realignment of a density matrix, then this gives you another permutation of the density matrix element. Okay, so I will come to this point, that what would be the permutation or what would be the arrangement, how to arrange the matrix element so that we can get the realignment. So this realignment criteria is given by here also two researchers independently. They have studied this entanglement detection problem with realignment criteria, and they are K. Chen and O. Rudolph. Okay, so they are independently studied this criteria. They have independently obtained this criteria. So it states that let us suppose for any bipartite separable state row, that means if any bipartite separable state is given to you, then the realigned matrix, that means row R, row is the density matrix, and in the superscript we have R. So this denote that the realigned matrix of the density realigned matrix of the given density matrix. And if we take the trace norm of this realigned matrix less than equal to 1, then we can say that this state is separable, or in the reverse way, that if this state is separable, then the trace norm of the realigned matrix is always less than equal to 1. Okay, so if you consider the contrapositive statement of this, then you can say that if the trace norm of rho r is greater than 1, then we can say that this state is entangled. So this is the realignment criteria. So I will come back to this point later. First of all, let me tell you that what would be the realignment operation. Okay, so realignment operation is, as I have said, that it is another kind of arrangement in the matrix elements. So again, let us consider the 2 qubit density matrix. So 2 qubit density matrix is given by this equation 9. And when we are considering the realignment operation, so realignment operation when we are performing on row 1, 2, so then the state looks like this 10. Okay, so how we have obtained this one? Just go to the again we can consider the total 4 cross 4 matrix can be split into 4 block matrices A B dagger and C. Now let us consider the first block matrix. That is, first block matrix is T11, T12, T12 star, T22. So maybe you can hear. Just see the first block matrix A. T11, T12, T12 star, T22. So what we have done in the realignment operation, we are just write this element T11, T12 star, T12 and T22. We can write this in a row. And when we are writing these elements in a row, we have to write the elements in this form. T11 first element, then second is T12 star, then third one is T12, and the fourth one is T22. Okay, so T11, T12 star, T12, T22, this can be written in a row. You just see here T11, T12 star, T12, T22. So this is written in a row. So that means it is another rearrangement of the matrix elements. Okay, so now come to this point, come to the second block matrix T13, T14, T23 and T24. So you can see here block matrix B, T13, T14, T23, T24. So you can write these elements in a row again. How to write these elements in a row? Just take the element T13, T23, T14 and T24. So just write this element in this way or in a row T13, T23, T14, T24. So if you write this in a row, then it will look like this. So T13, T23, T14, T24. In this way, you can write the third block matrix B dagger in a row and fourth block matrix D in a or C in a row. So when we rearrange when we consider the rearrangement of the matrix element in this way, then we are saying that we have performed realignment operation on the density matrix row 1, 2. So now the point is that this matrix can detect entanglement. Okay, so realignment matrix and the partial transpose matrix can be used to detect whether the state is entangled or not. But the problem is that can we use these operation in an experiment also? So can experimentalist realize this matrix in an experiment? This is the question we can ask. Okay, so when we are asking this question, so the obvious answer is no, we cannot apply it in the experiment. When we where is the problem when we apply this operation in an experiment? The problem is that these operators are positive. Partial transposition operators are positive operator, but not completely positive operator. Okay, and realignment operation is neither positive nor completely positive. That means there may exist some state for which row 1, 2 gives you all eigenvalues positive. That means it is it behaves like a positive operator. But there may exist some other state row 1, 2. That means the matrix elements are different. And then if you perform this row 1 realignment operation on it, that means when you are getting row 1, 2 this and again calculate the eigenvalues, then you can find that 1 or 2 eigenvalues may be negative. So what does this mean? This means that this this realignment operation is neither positive nor completely positive. So since the partial transposition operation is positive but not completely positive, realignment operation is neither positive nor completely positive. In any case, they are not completely positive operator. So both of these operators are not completely positive operator. Since they are not completely positive operator, so they cannot be realized in an experiment. It cannot be, because it cannot be written in terms of cross operators. Okay, because cross operators are very, very essential operators that may be implemented in the experiment. Okay, but if you are if you fail to show that whatever operation you are applying, they are not completely positive operator, then you cannot apply this operator in an experiment. So that means to apply the operator in an experiment, you have to show that the constructed operator must be a completely positive operator. So we are going to do the same thing here. So how to do this? So I am skipping these slides. Just I am giving you the sketch that how to do this, how to make a positive operator, how to make a positive operator to a completely positive operator. Okay, so Horodic and Kurt in 2002, they had given a method by which we can make a positive map, to completely positive map. Okay, so this SPA, that means structural physical approximation, this is the method by which we can make a positive map a completely positive map. Okay. So let me explain this method, structural physical approximation. So what is the idea behind it? The idea is that, let us consider a positive map phi. Okay, so if you have a positive map phi, and our task is to make this positive map phi a completely positive map. That means we have to transform the map phi to a completely positive map. We have to take phi to a completely positive map. Okay, so to do this, we have to make a mixture. Okay, so we can make a mixture of the given positive map and a maximally mixed state with some proportion. Okay, so what do you mean by maximally mixed state? Maximally mixed state means another word is called this maximally mixed state is also known as depolarizing state, and this mathematically it can be denoted by the identity operator. So that means you have to make a mixture with the identity operator and the given positive map in such a way, means you have to make the mixture in such a way such that the resulting map will be completely positive. So how to make this? So this proportion you are adding on positive map and the proportion you are imposing on maximally mixed state, this proportion will play a vital role in making the mixture completely positive. Okay, so you can see the equation 11. So in equation 11 you can clearly see that this is a D tensor D dimensional space. So in this equation 11 we are talking about the D tensor D dimensional system. So in D tensor D dimensional system we have the identity operator of order D square. So ID square represent the identity matrix of order D square, and here we are uh, adding this mixture proportion P star by D square. So P star by D square, this is the proportion adding to ID square, and 1 minus P star is the proportion adding to the positive map phi. Okay, so now we have to make this mixture in such a way, or we will get some critical value of P star such that this phi tilde rho will become a completely positive map. Okay, so because since phi, the positive map we are considering here, this is a positive map, id square, it is also a positive map. So that means the combination of these two positive map is maybe positive, maybe negative, but it depends on these proportions. So there exists some critical value of P for which this mixture will be positive. Okay, so Horonoki and Eckert, they had they derived this critical value of P for which this will become a completely positive map. Okay, so this means that we are now in a position to make a positive map to a completely positive map. So we this mapping make a positive map to a completely positive map. Okay, okay, so now we are done. So now the second thing is that, can we realize it in the experiment? Yes, we can realize it in the experiment, because the resulting map is a completely positive map, so we can realize it in the experiment. The second point, is that what would be the interpretation of it? Okay, so how we can interpret it? The interpretation of this SPA is that if you want to see the interpretation of this equation 11 in terms of eigenvalue, then we can only say that after applying this operation, or after applying SPA, when you are applying SPA, you will that means you are applying some transformation, you are working on some transformation, you are performing some transformation. So when you are performing some transformation, then you will get some output. Okay, and that output is nothing but this mixture. Okay, so the main task of this transformation is that the structure of the output of the non-physical map phi same. Okay, so the structure is not deviated after applying the structural physical approximation on the non-physical map phi. It keeps the structure of the vector same. Okay, but that means, what do you mean by structure? Structure means the vector, the direction of the vectors will remain same after applying this SPA. Okay, but what would be the key point here that makes the non-physical map, that means a positive map to a completely positive map, that bring a complete positive map to a completely positive map? The main thing here that changes the scenario, that means it transforms the positive map to the completely positive map. The main thing here, for the change of the length of the vector by some factor. So that means when you are applying SPA on some state rho, then it only changes the length of the vector. Okay, but keeps the direction of the vector same. This is the main theme of SPA. It does not disturb the direction of the vector, but it changes the length of the vector. It may increase, it may decrease. So how to find out the length of the vector? So the length of the vector is governed by this eigenvalue. Okay, so the eigenvalue is the main thing that we have to concentrate on. So now this is the main idea of SPA. So now when we apply this structural physical approximation on partial transposition map, because we know that partial transposition map is a positive map, but it is not a completely positive map. So we can apply this structural physical approximation on partial transposition map, so that we can make this partial transposition map a completely positive map. And if we do this, then we are capable of achieving this map in experiment also. So this work have been done by Ordoki and Eckert in 2002. So I'm not going on to this. Just we can mention here some application of SPAPT, structural physical approximation of partial transposition map. So here we have applied this structural physical approximation of partial transposition map in the estimation of optimal singlet fraction. So we have already, I already told you that the concept of teleportation. So in the concept of teleportation, this singlet fraction plays a vital role, and the value of singlet fraction we can obtain in experiment if we apply this SPA on partial transposition map. So we have shown in this paper, which is published in 2018. Then also we can apply this structural physical approximation of partial transposition map in the estimation of entanglement negativity of a 2-qubit quantum system. So we can estimate entanglement negativity is a measure of entanglement. Okay, so just using this measure we can say that how much the states are entangled. So to achieve this, the value of entanglement negative in experiment, we can apply this structural physical approximation of partial transposition operation. Okay, so this paper is published in 2018 also. Then also we have already seen that we can use this SPAPT in the detection of entanglement. Here we have done the SPAPT in higher dimensional system, that is qubit qubit system. So in the previous slides I talked about the qubit system, but SPAPT map can be applied on qubit system also. Not only that, in 3-qubit system we can have different classes of entanglement. So in the 2-qubit system we have only either the state is entangled or separable, but when you go to 3-qubit system, then we can have many types of entanglement. For example, the state may not be entangled, that means the 3-qubit system may not be entangled, that means the 3-qubit system are separable system. The 3-qubit system may be biseparable also, that means 3-qubit system in between any 2 qubit there may be entanglement and it is not entangled with the 3rd qubit. So you can do this you can have this concept for any 2 qubit from the 3-qubit system. So that means there exists biseparable system also. And in the third kind of entanglement is the genuine entanglement. That means there exists entanglement between all the 3 qubits. Okay, so these are the 3 ways by which we can discriminate the or which we can classify the 3-qubit system. So here in 2022 we have applied this structural physical approximation of partial transposition in the classification of this 3-qubit system. Okay, now come back to this realignment operation. So realignment criteria, which is a very powerful criteria in the sense that it may be used to detect negative partial transpose entangled state as well as positive partial transpose entangled state. So as we have said that partial transposition or criteria, positive partial transposition criteria is not necessary but sufficient in higher dimensional system. Okay, so in higher dimensional system, if some state is separable to if some state given to you is separable, then if you take the partial transposition of the density matrix, then you will get all eigenvalues are positive, but converse is not true. Okay, so there this type of entangled states whose partial transposition is positive but this state is still entangled, this type of entangled state are known as positive partial transpose entangled state. Okay, and these positive partial transpose entangled states are not detected by the partial transposition criteria, but this realignment criteria not only detect the negative partial transpose entangled state, but it can detect the positive partial transpose entangled state. Okay, so in this sense, this realignment criteria is more powerful than the positive partial transpose criteria. But the main problem with this realignment criteria is that it is neither positive nor completely positive. So this means that in spite of that the criteria is powerful, you cannot apply it in the experiment, you cannot achieve it through the experiment. Okay, so this is the main problem here. So we would like to overcome this problem just by approximating it to a firstly to a positive map and then to a completely positive map. Okay, so we again use the concept of structural physical approximation of partial transposition, structural physical approximation on realignment operation. So First of all, we will do this in 2 steps. In the first step, we will approximate the non-positive realignment map with a positive map. So that means, first of all, we will make the realignment map a positive map, and whenever we will have this positiveness of a realignment map, then we will talk about the completely positive map. Okay, then, or we will make it a completely positive map. So the structural physical approximation of realignment map, this transformation may be defined like this. Okay, R tilde rho. So R tilde rho is the structural physical approximation of realignment map. And again, it is a mixture of the depolarizing map and the realignment map. And P by D square is the proportion added to the depolarizing map, and 1 minus P by trace rho R rho, this is the proportion added to the realignment map. So after adding this proportion, we have a mixture of the realignment map and the depolarizing map. So when we do this, then we have to see whether we can have some value of P for which this R tilde rho will be positive map. And once we get the positivity of the R tilde rho, then we can talk about the completely positive map. Because when we are talking about completely positive map, first of all, we have to make the map positive. Okay, otherwise we cannot do it. So positivity of structural physical approximation of realignment map. So as I already told you that this R rho, the realignment map, may have negative or positive eigenvalues. Okay, so now let us consider this case 1. So suppose that all eigenvalues of R rho are non-negative. Okay, so let us suppose there exists some state rho for which R rho, that is realignment operation, when you are performing on rho, then all eigenvalues are non-negative. That means greater or equal to 0. In this case, you don't have to show that it is a positive map, because it is already there, it is already positive. So in this case, we have to show only that R tilde is completely positive map. But there exists other case also, where this realignment map, when operating on rho, then we can have either some this R rho may have negative and positive eigenvalues both. Okay, so when R rho have negative and positive eigenvalues both, this means that R rho is not a positive map, and since R rho is not a positive map, we have to make it positive first. Okay, so in this case, we can calculate, as I told you, that we have to calculate the value of P, which is given in this transformation. We have to calculate the value of P for which this map will give all eigenvalues positive. Okay, and then we this value of P can be expressed in terms of the moments, first and second order moments of R rho. Okay, so first and second order moment of R rho can be measured in experiment. That is why we have to express the probability or express the parameter P in terms of the first and second order moment. So I will tell you that when R tilde rho will be positive. So here written that R tilde rho may be positive under some condition. So we have derived the condition under which this R tilde rho will be positive. Okay. So once we have R tilde rho positive, then we will go for the completely positivity of R tilde rho. So now to show that R tilde rho is positive, that means all its eigenvalues are positive. All its eigenvalues are positive. So to determine the eigenvalue of some operator, first of all, what we have to do? So we have to find out the characteristic equation. Okay. So here we have, let us suppose, since we have d-dimensional system, so R rho has d square eigenvalues, because the matrix representing R rho is a d cross d matrix, so it has d square eigenvalues. So now we don't know which eigenvalues are positive and which are negative, and also we don't know how to calculate these eigenvalues because the dimensions are very large. So and we are doing it theoretically. We are not considering any particular form of rho. So we are giving this result for any arbitrary d-tensor d-dimensional system. Okay, so if we have any d-tensor arbitrary d-tensor d-dimensional system, so the characteristic polynomial which is required for to determine the eigenvalues, so the characteristic polynomial is given by equation number 19. So here you can see that we have a characteristic polynomial of order d square and of degree d square, and ak here represent the coefficients of each term. Okay, and this ak a0 you can find 1, but after that ak k equals to 1 to d square, they are all functions of eigenvalues of r rho. Okay, so they can be given in terms of eigenvalues of r rho. Okay, so this is a polynomial equation. Okay, fx equals to 0 gives you the eigen characteristic equation. Okay, so now here our focus is not to find out the specific eigenvalues, but we just need that how many eigenvalues are positive and how many eigenvalues are negative. If we find that all eigenvalues are positive, then we can say that the given r rho, this is a positive operator because all eigenvalues are positive. So that means we have to concentrate on the sign of the eigenvalues. Okay, so this can be done just by using the Descartes rule of sign. And using this Descartes rule of sign, we can easily find out that how many roots are positive and how many roots are negative. Okay, so here you can see the last point, the matrix R rho is positive semi-definite if and only if the number of sign change in the order list of non-zero coefficient of fx is equal to the degree of the polynomial fx. Okay, so let us suppose that you have second degree equation. Okay, let us suppose that ax square plus bx plus c equals to 0. This is a second degree equation. Okay, second degree equation. So and you find that this it has sign change appears in two places. So if sign change appears in two places, that means at most it has two positive eigenvalues. Okay, so in this way, so if we have at most two positive eigenvalues, then then we can say that all these eigenvalues, the eigenvalues are positive, and since the matrix R rho is positive semi-definite. So here we have used this result which is given in point number last point. The matrix R rho is positive semi-definite if and only if the number of sign change in the order list of non-zero coefficients of fx is equal to the degree of the polynomial fx. So if the number of sign change is equal to the degree of the polynomial of fx, this means that the all eigenvalues are positive, and since all eigenvalues are positive, we can consider that R rho is positive semi-definite operator. So this and also this non-zero coefficients, this ak, this ak are the non-zero coefficient. So this non-zero coefficients we need to determine so that we can tell that whether how many sign changes are there. Okay, so to determine the number of sign changes, we need to calculate these AKs. So the coefficients AKs we need to calculate, and so what we have done, we have expressed these AKs in terms of the moments of R rho. Okay, so since moments of R rho can be realized in an experiment, so this means that in an indirect way, we can say that all coefficients can be realized in an experiment. So here in equation 21 and 22, you can find that a1 is m1, that is first moment. A2 is equals to half of m1 square minus m2. That means the second moment and first moment, a combination of second moment and first moment. In this way, all the coefficient can be written in terms of all other moments. Okay, and since moments can be realized in an experiment, so these coefficients can also be realized in an experiment. So now after this idea, I'm giving you the main result of this work, that when we can say that the realignment matrix, that is R rho, is positive, is a positive operator. So this is the condition that the structural physical approximation of realignment map R rho is a positive operator. That means R tilde rho is a positive operator for P belongs to. So here is the critical value of P. So P is lying between, here P is not lying between 0 and 1, but there is a critical value L above which the P will lie, and the upper bound of P is 1. So that means L less than equal to P less than equal to 1, and this L is given equals to 0 when the minimum eigenvalue of R rho is greater or equal to 0, and minimum eigenvalue of R rho when less than 0, then L is given by this d square k by trace R rho plus d square k. Okay, so this L can also be determined because d, k all are known, and trace R rho, this is the first moment of R rho, so which can be realized in an experiment. So in this way we can say that L, the lower bound above which P will lie, so this lower bound also can be realized in an experiment. And one more thing, that this k, where k is the maximum of 0 minus lambda minimum eigenvalue of R rho, lower bound of minimum eigenvalue of R rho. So lower bound of minimum eigenvalue of R rho is totally defined in terms of the first moment. Okay, so that means this lambda minimum LB can also be realized in an experiment. So now to show that the experimental realization of the approximated map R tilde rho, it is not enough to show that R tilde rho is positive, but also we have to show that it is completely positive. So to show that it is completely positive, we have used this result by C. Kong and Y.T. Pun, which is appeared. This work has appeared in linear and multilinear algebra in 2011. We have used this result to show that this R tilde rho is completely positive. So 25, equation number 25 and 26 gives the condition for which we can say that this structural physical approximation of the realignment operation is a completely positive operator. So now after showing that this SPA of realignment operation is a completely positive operator, that means it can be realized in an experiment. So now our task is to give some entanglement criteria, entanglement criteria which is related with this R tilde or structural physical approximation of realignment operation. Okay, so here this R tilde rho set, this can be realized in an experiment. Trace norm of this, that trace norm of structural physical approximation of the realignment operation, this trace norm must be less than equal to P into trace R rho set minus 1 plus 1 by trace R rho set. So here you can see that all the quantities. So in the earlier slide we have already seen that the P, the small p, which is the parameter, it is realized in an experiment. This trace R rho, which is the first moment of the realignment operation, which can be realized in an experiment. So this means that the left right hand side is totally achievable in an experiment. So we can achieve this result in an experiment. Okay, so this is the criteria. So this criteria is only the necessary condition, that if the condition, if any quantum state described by a density operator is separable, means if you are given some separable density operator, then this condition hold. Okay, so but the question is that if you know that if you already know that this state is separable, then what is the value of this criteria? Because you already know that this state is separable, but our task is to show that whether the given state is separable or not. Okay, so this means that we have to use its contrapositive statement, which will be useful here. Okay, see, the contrapositive statement is this, that if the trace norm of R tilde rho is greater than this quantity, then we can say that the state is entangled. That means we can use this inequality 28, which is the contrapositive statement of 27. If this inequality holds, then we can say that the given state rho is an entangled state. Okay, so the given state is an entangled state if this inequality hold. So in this way, the result 27, which is the separability criteria, and result 28, which is the contrapositive statement of 27, which is the entanglement criteria. Okay. So now one thing is that here you can see that for any separable state, if you are considering any separable state, then this trace or row shape, this must be equal to 1. You can see that this derivation is given in the paper. The trace row r shape equals to 1, and if it equals to 1, then we have norm of r tilde, that is norm of this trace norm of this structural physical approximation of the density operator, that must be less than equal to 1. Okay, so now one interesting thing is that we find a class of state which is known as Smith symmetric state. So if we are considering the Smith symmetric state, and if we would like to find out whether this state is entangled or not, so here you can see that this state is defined in terms of the operator. So AIs denote the orthonormal basis of the operator space, and lambda I denote the non-negative real number known as Smith coefficient. So if this state is given in terms is like this, which is known as Smith symmetric state. This state can be when we are going to identify or detect this state, whether this state is entangled or not, just by using our criteria, then we find that our criteria reduces to the original realignment criteria. So that means this criteria will reduce, criteria 27 and 28 will reduce to the original realignment criteria for this particular class of Smith symmetric state. So now let us illustrate this criteria, our criteria, just by using an example. Okay, so you can just use this example. This example is given in this paper, Horodoki's paper in 1997. They had given it. So this is a bound entangled state. That means this is a positive partial transpose entangled state. Okay, so here we will positive partial transpose entangled state. This means that this state cannot be determined by the positive partial transposition criteria. So PPT criteria fails here. So PPT criteria fails here, and we would like to use realignment criteria to detect whether this state is entangled or not. And we will use this realignment alternative form of the realignment criteria, which is given here, given in equation 27 and 28, because it is an experimentally realizable criteria. So here we find that for some alpha goes from 0 to 1. So here 0.1 to 9 we have taken, and we find that the theorem 2, which is the separability criteria here, theorem 2, which is violated. So theorem 2 is violated. This means that corollary 1 is true, and since corollary 1 is true, this means that it indicate that this state rho alpha is entangled for all for alpha 0.1, for alpha equals to 0.2 up to 0.9. And here also we had given the range of P also. So in this range of P means here the mixture, the proposition of the mixture, this P, equation number 18, we have the P here, which is the proportion of the mixture. So if the proportion of the mixture is lying between this, and for alpha equals to 0.1, the theorem 2 is violated. That means this state is entangled, and in this way for all other values of alpha. And I have already discussed that that first moment of R rho can be estimated experimentally. So here here we have just we have given how to estimate the first moment of R rho in an experiment. Okay, so to do this, let us consider a quantum state rho AB, a d cross d dimensional system, and this we are using the result of 2018. This result is obtained by Gray, Banchi, Bath, and Bose, and here it has been shown that the measurement of moments of a partial transpose matrix is technically possible using m copies of the state rho AB and swap operation. So that means they have obtained this result for partial transpose matrix. Okay, but we are working on realignment matrix. Okay, so we will use this result, this the technique they have used there to determine the first moment of our row experimentally. Okay, so we have constructed the permutation operator, which is given by equation 33. So here in the first moment is given, and one more thing is that uh, they have calculated the moments of a partial transpose matrix in an experiment just by using m copies of the given state rho AB. So if m copies means more than one copies, if more than one copies are given to you, then only you can you can perform the or you can achieve the moments of a partial transpose matrix in an experiment. But in our case, we need only single copy of the realigned matrix. So only single copy of realigned matrix is enough to estimate the first moment of our row in an experiment. So to do this, we have just used the permutation operator P in the first moment, and then we have derived that the first moment can be written in terms of the first moment of r tilde, because the first, here you can see the two thing, the first moment of r rho abp. So here just observe that r rho ab, this is the realignment operation, and it is neither positive nor completely positive for some density matrices. Okay, so this means that you cannot achieve this value in an experiment. Okay, so what we have done, we have just transformed this r rho ab in terms of, we have write this r rho ab in terms of the r tilde rho ab. So r tilde rho ab, we have shown that it is positive and it is completely positive. So that means r tilde rho ab can be achieved in an experiment. Okay, so this is the thing we have done here. So m1 is written in terms of trace of r tilde rho ab into p minus k by m1 plus d square k, and already we have shown that k, m1 and trace r tilde rho p, they are all experimentally realizable quantities. So the upper bound of m1 is a realized. So we can estimate the first moment of r row in an experiment. So this is the final result of m1. This is totally mathematical. Okay, so this SPA can be used in the quantification of entanglement also, but I am not. I would like to stop here because I am not. I will not discuss this thing, quantification of entanglement using SPA, because it will take a lot of time to explain. Thank you.
Thank you, sir. Thank you everyone for your active participation and engagement in session 4. A big thank you to Dr. Satyavrat Adhikari sir for his insightful presentation on quantum information processing applications. Thank you so much, sir.
Thank you, sir. Any question?
Participants, if you have any question, then ask. Participants, if you have any question, write in chat box your question. I think no question, sir. Thank you so much, sir.
Okay. Okay, thank you very much.
Participants, please wait for feedback link. Participants, please fill the feedback form for session 4. The meeting link is open up to 9:05 p.m. You can fill the feedback form as early as possible. So feedback form is available in chat box. Participants, tomorrow's session is quantum gate model for transport industry to optimize the routes. And the resource person is Dr. Kumar Gautam, Associate Professor WIPS. So join the tomorrow's session on time. Thank you.